So here we have a question that says, in an experiment between A and B, the initial rate of reaction was found for various starting concentrations of A and B. So here we had three different experiments, okay, where we varied the concentrations of A or B, right? Calculate the individual orders for A and B, the overall order, the value of the rate constant, as well as the units of the rate constant. Now what they're telling us here is that we had a reaction, right, in which A and B were reactants, and they reacted to form some products. And we want to find, the first thing we want to find is the individual orders for A and B. So first, if we want to find the order with respect to A, we can compare experiments 1 and 2. We want to know how varying the concentration of A affects the initial rate, right? We want to see how varying the concentration of A affects the initial rate. So if we look at experiments 1 and 2, right, experiments 1 and 2, what we see here is that we've tripled the concentration of A, right? We have the same concentration of B. So we've ensured that the concentration of B has no effect, right? Because we're keeping the same concentration. And what we see here is that the rate has been tripled, right? So tripling the concentration of A triples the rate. So I can say, if I compare experiments 1 and 2, I've tripled the concentration of A and I have also tripled the rate as a result, right? I've also tripled the rate as a result. So what that means is that the reaction is order is equal to 1 with respect to the concentration of A, right? That the rate is directly proportional to the concentration of A. So what that means over here is that if I triple the concentration of A, I'll triple the rate. If I double the concentration of A, I would have doubled the rate. The next thing I want to do is I want to figure out the order with respect to B. For that, we can compare experiments 1 and 3. If we look at experiments 1 and 3, from experiment 1 to experiment 3, we kept the same concentration of A as we had in experiment 1. So we're saying here that, okay, changing the concentration of A will have no effect on the rate because we have the same concentration, so we haven't really changed it. Whereas we know that we've doubled the concentration of B, right? So if we look at experiments 1 and 3, right, what we can see here is that we've kept the concentration of A constant. So what we've done is we've doubled the concentration of B, right? And what's happened to the rate? We've increased the rate of the reaction by a factor of 4. We've increased the rate of a reaction by a factor of 4. So if we look at experiments 1 and 3, what we've done is we've doubled the concentration of B, and what we realize is that the rate has quadrupled. So what that means over here is that the reaction is order 2 with respect to B. The order is equal to 2 with respect to B, with respect to the concentration of B. What that means is that if I double the concentration of B, the rate changes by a factor of 4. So what that means is that, what that means over here is that the rate is proportional to the square of the concentration, right? If I double the concentration, the rate changes by a factor of 2 squared. If I triple the concentration, the rate would have changed by a factor of 9, right? 3 squared. We're going to raise the change in concentration to a certain power. Okay, so order 2 means that the change in concentration was by a factor of 2. So therefore, the rate changed by a factor of 2 to the power of the order, which is 2. So the rate changed by a factor of 4. Okay, if I triple the concentration, then that would mean that the rate would have changed by a factor of 3 to the power of 2, which would have been 9. Okay, it would have been 9 times faster. So now we've determined the individual orders, right, for A and B, right? We've determined the order with respect to A, and we've determined the order with respect to B. So what's the overall order for this reaction? What's the overall order? The overall order is simply 3. It is the sum of the individual orders. It is the sum of the individual orders of each reactant. So if we just add up the orders with respect to each reactant, it's order 1 with respect to A, it's order 2 with respect to B. So the overall order for the reaction is 3. Now if you look at the rate equation, here, the rate equation looks like this. The rate is equal to K times the concentration of A to the power of 1, because it's order 1 with respect to A, times the concentration of B to the power of 2, because it's order 2 with respect to B. So now we can use the rate equation. To find the value for the rate constant as well as the units of the rate constant over here. Okay, so we know that the rate equation is rate is equal to K times the concentration of A times the concentration of B squared. So we can take data from any of the experiments and plug that in to the rate equation to find the value of K. So let's just take data from experiment 1. If I take data from experiment 1, the rate is equal to 2, right? The rate is 2, and this is equal to K times the concentration of A, which is 0.5, times the concentration of B squared, so that will be 1 squared, right? And K comes out to 4, right? I've just taken data from experiment 1. The rate is 2 moles per dm cube per second. The concentration of A is 0.5 and the concentration of B is 1. Okay. Now, what are the units of K? What are the units of K? Right. If you look at the units of K over here, right, the units are, we have rate divided by concentration cubed. Right. The units are rate divided by concentration cubed. Right. Here, the units of the rate constant are simply rate divided by the concentration to the power of the overall order. Okay, rate divided by concentration to the power of the overall order, right? So what we have over here is the units for rate will always be moles per decimeter cube per second or per minute, right, depending on what's given to you, divided by concentration cube, which is mole cube dm to the power of minus 9, right? Mole cube dm to the power of minus 9. So what does that come out to? We have mole to the power of 1 divided by mole to the power of 3, that is mole to the power of minus 2, right? 1 over mole squared, that's mole to the power of negative 2, dm to the power of 6 per second. So here this is the value of K with its units, right? So here we have the next example, which says that in an experiment between C and D, the initial rate of reaction was found for various starting concentrations of C and D. Calculate the individual orders for C and D, the overall order of the reaction, the value of the rate constant, and the units of the rate constant. So over here, we're first going to calculate the individual orders for C and D, okay? And in order to calculate the individual orders, right, we're going to start with trying to find the order for C, right, for reactant C over here. And we can see over here that if we compare experiments 1 and 2, what we're doing is we're changing the concentration of C, but we're keeping the concentration of D constant. So we want to know what effect does changing the concentration of C have on the rate. So if we compare experiments 1 and 2, what we can see over here is that if I halve the concentration of C, right, because I'm going from 0.4 to 0.2, the rate changes by a factor of 0.04 divided by 0.16, right? So it changes by a factor of, the rate changes by a factor of what? 1 over 4. So the question here is, again, concentration to what power? So 1 over 2 to what power gives you 1 over 4? We know that 1 over 2 to the power of 2, 1 over 2 to the power of 2 gives me 1 over 4. So here the order is 2 with respect to C. Alternatively, you can say, here, to make it easier for ourselves, right, we can say that if we look at experiment 1 in comparison to experiment 2, the concentration of C is double that of experiment 1, right? In experiment 1, we have double the concentration of C that we do in experiment 2. And here we can say that if I double the concentration of C, the rate is 4 times as much, right? Instead of 0.04, it's 0.16. The rate is 4 times as much, right? The rate is 4 times as much, right? The rate is 4 times as much. So over here, I can say 2 to the power of what gives me a change of 4, right? Doubling the concentration changes the rate by a factor of 4. So 2 to what power gives me 4, and we can say therefore the order is equal to 2, right? 2 squared is equal to 4. So the order is equal to 2 with respect to C. Now we want to figure out the order with respect to reactant D, right? For reactant D, we can compare experiment 1 and 3. Because experiments 1 and 3, we're keeping C constant. Now we just want to know the effect of changing the concentration of D, right? So if we compare experiments 1 and 3, okay, what we see over here is that if I triple the concentration of D, right? if I triple the concentration of D from experiment 1 to experiment 3, we went from 0.4 to 1.2, then the rate is multiplied by a factor of 1.44 divided by 0.16, right, which is 9, right, this is 9. So the rate is multiplied by a factor of 9. So 3 to the watt power gives me a change of a factor of 9. Again, it's 3 squared is equal to 9. Tripling the concentration changes the rate by a factor of 3 squared. So the order is 2 with respect to D as well. So we can say that this reaction is order 2 with respect to D. Then what's the overall order for this reaction? The overall order for this reaction is order 4. Right? You're going to add up the individual orders of each of the reactants. So it's order 2 with respect to C, order 2 with respect to D. So the overall order is just 2 plus 2. So the overall order here, is equal to 4. So over here then we can say that the rate equation, the rate is equal to K times the concentration of C, the whole thing squared, times the concentration of D, the whole thing squared, right? It's order 2 with respect to C, raised to the concentration of C raised to the power of 2, and it's order 2 with respect to D. So the concentration of D is also raised to the power of 2 in the rate equation. Okay, so this is your rate equation here. And now we want to find the value of the rate constant. So you can take data from any one of these experiments to find the value of the rate constant. Okay, so let's just take data from experiment 1. Let's take data from experiment 1. Right, from experiment 1 we know that the rate is equal to 0.16. So the rate is 0.16, and the rate is equal to K times the concentration of C squared times the concentration of D squared. Right, so we have 0.16 is equal to K times the concentration of C squared, that's 0.4 squared, times the concentration of D squared, which is also 0.4 squared. Then what is the value of K here? The value of K over here comes out to 6.25. Now we want to find the units of K, right? Now for the units of K over here, we can say that the units are equal to rate divided by concentration to the power of 4. Rate divided by concentration squared times concentration squared, right? So we have rate divided by concentration to the power of 4. Again, the units for the rate constant will be rate divided by concentration to the power of the overall order. Here the overall order is equal to 4. Okay, so we get moles per dm cube per second. Those are the units for rate always, right? Change in concentration over change in time. We're going to divide that by concentration to the power of 4, which is mole to the power of 4 dm to the power of minus 12. Okay, so the units over here come out to mole to the power of negative 3, that's 1 minus 4, minus 3 minus minus 12, so dm to the power of 9 per second. So those are the units of K over here. So you have 6.25 mole to the power of negative 3 dm to the power of 9 per second. The next question that we have says, in an experiment between E and F, the initial rate of reaction was found for various starting concentrations of E and F. And again, we want to calculate the individual orders, the overall order of the reaction. We want to find the rate equation and the value of the rate constant K and the units of the rate constant as well. So now we're going to start by trying to determine the individual orders for E and F. Okay? So we start with trying to determine the individual order for E. We want to take two experiments in which we're keeping the concentration of F constant. So we can see here that we're changing the concentration of F in all three experiments. So we're not really keeping F constant in any of them. So we can't really determine it for E first. Okay, so let's determine it for F. Alright. So for F over here, we can look at experiments 2 and 3. Because in experiments 2 and 3, we're keeping the concentration of E constant, and we're only going to see what changing the concentration of F, right, what effect that has on the rate. Right. So if you look at experiments 2 and 3, right, experiments 2 and 3. So if we look at experiments 2 and 3 here, we're changing F by a factor of 1.5, right? F is multiplied by a factor of 1.2 divided by 0.8. So F is changing by a factor of 1.5, right? F is changing by a factor of 1.5, and the rate doesn't change, right? The rate is unchanged. It remains the same. So changing the concentration of F has no effect on the rate. Changing the concentration of F has no effect on the rate here. So we can say that therefore it is order 0 with respect to F. Order 0 with respect to F. Okay, because changing the concentration of F has no effect on the rate. Now in order to determine the order with respect to E, right, we can just look at experiments 1 and 2 since we're changing the concentration of E over here. So if we look at experiments 1 and 2, okay, we can see that we're doubling the concentration of E, right? The concentration of E is multiplied by a factor of 2, double the concentration of E, right? And the rate changes by a factor of 2 as well. Now we're also doubling the concentration of F, but we've already determined that changing the concentration of F has no effect. It has no effect on the rate. So we know that even though I'm doubling the concentration of F, this is having no effect on the rate because I've determined the order with respect to F. So I know that only the concentration of E is affecting the rate here. Okay, so doubling the concentration of E, right? I see that rate is multiplied by a factor of 0.32 divided by 0.16, right? So this is multiplied by a factor of 2. So then I can say that it is order 1 with respect to E. With respect to E. The overall order for this reaction is just 1, right? 0 plus 1. The overall order for this reaction is 1. The overall order is equal to 1, right? The rate equation for this reaction is rate is equal to K times the concentration of E. Okay? It will be concentration of E to the power of 1, E to the power of 1, and concentration of F to the power of 0. So it doesn't show up in the rate equation. Anything to the power of 0 is just 1, right? So it won't be F to the power of 0 would just be 1. So this is the rate equation that you have. And then you want to find the value of the rate constant. So take any experiment and plug in the values, right? So we can take experiment 1 again. We take experiment 1. The rate is 0.16 and this is equal to K times the concentration of E, which is 0.4. And you get K is equal to 0.4. And the units for K are simply rate divided by concentration, right? So the units for K, right, the units are rate over concentration, which is moles per dm cube per second, moles per dm cube per second divided by moles per dm cube, okay? And just the moles per dm cube and moles per dm cube cancel each other out, so the units over here are per second. The units over here are per second. So here we have the next question, which says that in a series of experiments, the reaction was carried out with different concentrations of the 3 reagents, and the following relative initial rates were obtained. Okay, so here we have a reaction between a ketone and HCN to form a hydroxynitrile, right? This is a nucleophilic addition reaction, nucleophilic addition. Remember, addition of HCN to carbonyl compounds, right? And what we want to know is we want to know the order with respect to each of these reactants, and I want to find the rate equation. So what is the rate equation for this reaction? What is the rate equation for this reaction? So over here, in order to find the rate equation, we're going to find the order with respect to each of the reactants, right? So first, let's find the order with respect to the ketone. Let's find the order with respect to the ketone here. For that, we can compare experiments 2 and 4. Okay, in experiments 2 and 4, what we're doing is we're changing the concentration of the ketone, so we're keeping the concentration of H plus and the concentration of cyanide ions constant. Okay, so in experiments 2 and 4, what we're doing is we're saying that the concentration of the ketone, right, the concentration of the ketone, that's CH3 twice CO, right, changes by a factor of 0.025 divided by 0.02, right? So we go from 0.02 to 0.025, so it's changing by a factor of 1.25. Right? The concentration is changing by a factor of 1.25, and the rate changes by a factor of 1.042 divided by 0.833. 1.042 divided by 0.833. So this is also a factor of roughly 1.25, right? So we have the concentration of the ketone changing by a factor of 1.25 and the rate changes by the same factor. So we can say that therefore the order is equal to 1 with respect to the ketone. The order is equal to 1 with respect to the ketone. The reaction is order 1 with respect to the ketone. Next we want to determine the order with respect to H plus, right? The concentration of H plus over here. So we're going to make sure that we keep the concentration of the other two reactants constant. So for that we can compare, we want to change the concentration of H plus, we want to keep the other two constant. So we can look at experiments 1 and 3, right? 1 and 3 we're keeping the ketone concentration constant and the cyanide concentration constant. So we're changing the concentration of H plus, right? So if you look at experiments 1 and 3, looking at experiments 1 and 3, looking at experiments 1 and 3, what we see is that we're changing the concentration of H plus by a factor of 0.05 divided by 0.06, right, which is 0.833. Okay, so we're changing the concentration of H plus by a factor of 0.833 and the rate is unchanged. It has no effect on the rate. So the changing the concentration of H plus has no effect on the rate, right? So therefore we can say that it is order 0 with respect to H plus ions, right? It is order 0 with respect to H plus ions. The reaction is 0 order with respect to H plus ions. Now we want to find the order with respect to cyanide ions, and for that we can compare experiments 2 and 3. Right? If we look at experiments 2 and 3, we're changing the concentration of cyanide, but the concentration of H plus and ketone remain the same. Right? And anyways, we know that changing the concentration of H plus will have no effect on the reaction anyways. Okay, since we know that it's order 0 with respect to that. If we look at experiments 2 and 3, right, we can see here that the concentration of Cn minus ions, right, changes by a factor of 0.06 divided by 0.05. So it changes by a factor of 1.2, right? And the rate over here changes by a factor of 1.00 divided by 0.833. So this is roughly also a factor of 1.2, right? So whatever factor we're changing the concentration of cyanide ions by, the rate is being affected by the same factor. So we can say that it is order 1 with respect to cyanide ions, right? So then my rate equation here is rate is equal to K times the concentration of the ketone, that is CH3 twice, right, CO, times the concentration of cyanide ions. H plus ions, the concentration of H plus will not show up in the rate equation because it's order 0 with respect to H plus ions. So this over here is my answer. This is my rate equation. So now let's look at the next example here. Okay, so here I have a reaction taking place between A and B to form some products. Okay. A and B are reacting to form products. Okay, so A and B are the reactants here. And what I want to do is I want to find the rate equation. I want to find the rate equation for this reaction. So I want to find the rate equation for this reaction. The rate equation is simply rate expressed as a product of the rate constant times the concentration of A to some power times the concentration of B to some power, right? Here M is the order with respect to A and N is the order with respect to B. So what we want to do here is we want to find M and N. Okay, if we want to find the rate equation, we want to find the order with respect to A and the order with respect to B. So here, if we look at experiments 1 and 2, right, we have experiments 1, 2, and 3. We've carried out 3 different experiments and we've monitored the initial rate here, right, or we've determined the initial rate for each of these experiments, right. We can easily find the order with respect to A. If we look at experiments 1 and 2, right, we're changing the concentration of A, but we're keeping the concentration of B constant. So we can say, if we look at experiments 1 and 2, right, look at experiments 1 and 2, we can say that the concentration of A, right, is multiplied by a factor of 0.3 divided by 0.6, right? The concentration of A changes by a factor of 0.5 or 1 over 2. Concentration of A changes by a factor of 1 over 2, whereas the rate changes by a factor of, we go from 1.3 into 10 to the power of negative 3 to 3.25 into 10 to the power of negative 4. So change by a factor of 3.25 times 10 to the power of negative 4 in experiment 2 divided by 1.30 times 10 to the power of negative 3. So it changes by a factor of 0.25 or 1 over 4, right? So what we're saying here is that we're halving the concentration of A, right? Concentration of A is 1 over 2 times in experiment 2 than it was in experiment 1, and the rate is decreasing by a factor of 4, okay? We times the concentration of A by 1/2 and the rate changes by a factor of 1 over 4. So therefore, we can say that it is order 2 with respect to A. Okay, it is order 2 with respect to A, right? Because 1 over 2 to what power gives you 1 over 4? 1 over 2 squared is 1 over 4. We can also say that if we double the concentration of A, right, from experiment 2 to 1, right, if we double the concentration of A, the rate becomes 4 times as fast, right? Experiment 1 is 4 times faster than experiment 2 because the concentration of A in experiment 1 is double that in experiment 2. So we've determined the order with respect to A here. We determined the order with respect to A over here, right? Now we need to determine the order with respect to B. Now if you notice, right, we can see that the concentration of A is different in each of the 3 experiments. So it's not like we're keeping the concentration of A constant in any of the experiments. So it's not very straightforward to determine the effect of the concentration of B. So we can just take any 2 experiments where B is changing. So let's just take experiments 2 and 3. Okay. So if we take experiments 2 and 3, what we see is that the concentration of A is changing by a factor of 1 over 2, right? The concentration of A is changing by a factor of 1 over 2, right, or 0.5. And the concentration of B is changing by a factor of 1.5, right? We're going from 0.5 to 0.75. And the overall rate over here changes by a factor of 1.83 times 10 to the power of negative 4 divided by 3.25 into 10 to the power of negative 4. So what factor does the rate change by? What factor does the rate change by over here? The rate over here changes by a factor of 0.56. The rate changes by a factor of 0.56. Now, we know that the concentration of A has an effect on the rate, right? Because we determined the order with respect to A, and we know that the concentration of B has an effect on the rate. That's what we want to determine. We don't know the effect that the concentration of B has on the rate. We want to determine the order with respect to B. Now, we know that it's order 2 with respect to A, right? Because we know that 1 over 2 squared is 1 over 4, or 0.5 to the power of 2 gave us 0.25. So we know that halving the concentration of A changed the rate by a factor of 0.25. So with order 2 with respect to A was 0.2. Again, what power raised to 0.5 gives us 0.25? And we know that's order 2, okay, because the power is 2 over here. So we know that from experiment 2 to experiment 3, if I'm changing the concentration of A by a factor of 0.5, the rate is affected by a factor of 0.5 squared. That's the effect that A has on the rate, right? And I know that the overall effect on the rate over here is 0.56. The overall effect is that the rate is changing by a factor of 0.56. But we don't know the effect of changing the concentration of B on the rate. The product of the effect of the concentration of A on the rate and the concentration of B on the rate is the overall effect on the rate. Okay, the product of the 2 effects is the overall effect, right? We know, okay, we're halving the concentration of A, so the rate will change by a factor of 0.5 squared. So it's order 2 with respect to A. We don't know the effect that B has on the rate, and we know the overall effect on the rate, right? We just took the ratio. So then what does X come out to, right? The product of the 2 effects on the rate gives you the effect of B on the rate. X over here comes out to 2.25. X comes out to 2.25. So multiplying the concentration of B by a factor of 1.5 meant that the rate was multiplied by a factor of 2.25. So 1.5 to what power gives you 2.25? So here we can say that we know that 1.5 squared You know that 1.5 squared is equal to 2.25. So therefore, we can say that it is order 2, with respect to B. Okay, it is order 2 with respect to B. So here we can say that the rate equation is equal to K times the concentration of A squared times the concentration of B squared. Okay, so this is your rate equation. This is your final answer. So again, what we did was we had 3 different experiments with varying initial concentrations of A and B, and we determined the initial rates for each of these experiments. Now you could easily determine the order with respect to A, because in experiments 1 and 2, we didn't change the concentration of B. We didn't change the concentration of B, all we did was we halved the concentration of A, right? So in experiments 1 and 2, what we did was we halved the concentration of A, right? We went from 0.6 to 0.3, and the rate decreased by a factor of 4, right? Concentration of A changed by a factor of 1 over 2, rate decreased by a factor of 1 over 4. So 1 over 2 to what power gives you 1 over 4? 1 over 2 to the power of 2 gives you 1 over 4. So it's order 2 with respect to A. You can also say in experiment 1 we have twice the concentration and the rate is 4 times as much in experiment 1 than it is experiment 2. So 2 to what power gives you 4? It would be 2. So it's order 2 with respect to A. Okay. Now what we see here is that the concentration of A is different in all 3 experiments. So we can't do the same thing for B as we did for A. So if we just took experiments 2 and 3, take any 2 experiments where we're varying the concentration of B. We took experiments 2 and 3 here, and we said that, okay, we're changing the concentration of A by a factor of 1 over 2, right, 0.5, and we're changing the concentration of B by a factor of 1.5. And the overall effect on the rate is changing by a factor of 0.56, right? Now we know that it's order 2 with respect to A. So changing the concentration of A by 0.5, right, decreases the rate by 0.25. That's 0.5 squared. So this is the effect that changing the concentration of A has on the rate. We don't know the effect that the concentration of B has on the rate. So we want to determine that. That's our unknown. And the product of the effect of the concentration on A and the effect of the concentration of B, right? The product of the 2 effects of A and B is the overall effect that we have on the rate. So from that we can determine the effect that changing the concentration of B by a factor of 1.5 has on the rate. Okay, changing the concentration of B by a factor of 1.5 changes the rate by a factor of 2.25. 1.5 to what power gives you 2.25? 1.5 squared is 2.25. Right? 1.5 to the power of 2. So therefore it is order 2 with respect to